To be that one person who welcomes you after lunch break can be a tricky challenge, but I hope you enjoyed your meal and you're not too tired, because I'm absolutely thrilled to guide you through the next topic, which is an exciting topic that's already keeping us extremely busy these days, and it also will be in the near future. Due to the fact that we have economical changes, we have climate change, we have ever increasing prices due to high inflations. In some cases, it forces us, but on the other hand, it also gives us the opportunity and the offer to take new and sustainable paths. And this is what I would like to show you with the topic right now. It's WFI production by energy-saving method, membrane-based. So that means it is a comparison of the classic way to produce WFI by using a multi-effect still compared to a modern state-of-the-art way, which is using a reverse osmosis system. A question from my side, is there anybody here who has ever experienced water treatment systems, worked with them? Wonderful. Okay, a few of you. Perfect. I'd like to show you the alternative way, producing WFI, and how this could look like. And on top of that, how this affects the footprint of the system within your company, the entire system investment for such a system, the documentation and qualification of such systems, and the general running costs. Before I delve a little bit deeper into... Does it work? No? No? Okay. Before I delve deeper into the details of these different technologies, I would like to show you some interesting facts and figures that should not only erase your curiosity, but above all, it also shows the enormous potential that we have in this kind of technology. So starting with the first number, in the comparison between cold production of WFI with multi-effect still, we have approximately 25 to 30% less investment costs, CAPEX. On the other hand, OPEX, we have approximately 75% less energy consumption between the cold way and multi-effect stills. And last but not least, approximately 30% less running costs for service and maintenance compared to both ways of manufacturing WFI. Let's take a look at a few facts about WFI using multi-effect distillation. And at this point, I would like to say one thing. Whether membrane-based WFI makes sense for your own production or not has to be decided individually. So there are some, let's say, information around that we have to collect, we have to come together, and we have to talk about this topic to find out whether the cold way of producing WFI is the right way for you. It may well be that hot manufacturing will be the right way for you to go, but this we will find out later on during the presentation. It's a safe process in terms of technology, as well as ensuring a microbiological purity through the high temperatures of the multi-effect stills, of course. And on the other hand, the system technology has been tried and proved for decades, so we know that it is safe. And also in the handling of those systems, you can make little mistakes, and through the high temperatures, nothing will happen in terms of microbiological contamination. On the other side, a WFI distillation system requires an upstream process, and I'm, from the pharmaceutical point of view, try to see everything through the GMP glasses. And when I'm talking about an upstream process, I mean that we have at least a reverse osmosis system to produce purified water in the upstream before to feed the distillation system. And therefore, we have two different ways. Purified water, according to Annex 1, is at least that we have a microbiological barrier before we entering the distillation system. And purified water, let's say state-of-the-art according to pharmacopoeia, means purified water according to a qualified system. That's why most companies that produce WFI by multi-effect stills therefore have two different water qualities that they have to qualify, of course, and which needs to be maintained and serviced separately to each other. And then, of course, the distillation process requires a very high amount of energy, which became a great topic for all of us. What kind of systems are required for producing WFI by using distillation? And my assumption is that we produce purified water as a required upstream process. That means that we have to make sure that we produce purified water in a proper way. That means we have the pre-treatment, we have the filtration and softening system. From our point of view, and that's kind of our philosophy, we made everything out of stainless steel 316L to be able to do a separate hot water sanitation in each of those production units. Then, of course, we need reverse osmosis with membrane degassing and EDI. So even this decision is made individually. It depends on the feed water quality and even some more points. And in this case, through the GMP glasses, we would need our own qualification package for purified water systems, and if necessary, also for storage and distribution, because most of the companies also use purified water quality for other purposes, like cleaning purposes or even for production. That means that we need another step for water for injection, which will be then the pressure column distillation system. We manufacture those systems from 1 up to 8 columns, which means from 50 liters per hour up to 9 cubic meters per hour. We need the upstream process I've mentioned before, and we would need our own qualification package for WFI, even with the storage and distribution systems. And on top of that, if required, you would also need the clean steam generator if you're not able to do that with the multi-effect still, which also requires an own qualification package in this case. So that means even for, let's say, project times, for lead times, we have to do different qualification packages, and for installation and startup, we also have to do, let's say, calibration, qualification, IQ, OQ for 3 different steps, which takes a lot of time, of course, and which also costs a lot of money. What does it mean for footprint, to make it a little bit more visual? So footprint for WFI by distillation means the first step is that we probably would need a softening system with maybe even further details in the pre-treatment compared to the feed water quality that we have. The second step is that we would need a reverse osmosis system, of course, to create purified water quality. If necessary, we would also need a storage and distribution system. On top of that, probably a clean steam generator. And of course, with the reverse osmosis system, we would supply the distillation system to create WFI with another storage and distribution system in this case. So the question is, what would be the alternative in this case? The alternative is that we would use the modern and state-of-the-art process for producing cold WFI by the membrane processes. It is actually, if we would go one step back, it is a very safe and robust and actually equal technology to what we know from the distillation process. Of course, we do not reach such high temperatures, but from the water quality, which is highly purified water, we already know that this kind of technology is pretty reliable. It is a system, or all those cold WFI systems that we have in use worldwide meet all requirements and regulations by ISPE, FDA, and EMA. And on top of that, we already have approved systems for human vaccine productions running in Germany by the acceptance by the German authorities. And this is a very important point, at least from my point of view, because Germany is a very overrated and over-regulated system in terms of rules for rules and for rules. And if you get approval in Germany, you would probably get approval everywhere. One of those systems are even in production for a COVID-19 vaccine at the moment. What else do we have? So the systems need the highest possible production capacities, and this is actually the beginning of my presentation when I said a cold WFI production is maybe not the right way for your own production, because it wouldn't make sense to choose the cold WFI production when you just have a requirement of like 5 hours per day where you would need WFI, and 19 hours per day would be in standby mode. So that means that the plant and production capacity, the size of the plant, and the design itself needs to be clarified. And of course, it needs a certain training and concept for the personnel who is working on those systems. What we absolutely recommend is a joint risk workshop that we held in advance with all departments that are involved in such a project to create a very early identification of everyone who is working on those projects, and to make sure and to address to the project whether there are maybe any internal or external influences, like regulations for your own authorities, regulations from your own company that you would like to add in this project. And therefore, we do also have joint risk workshops to identify, let's say, all the risks coming from the left and to the right. But at the end of the day, and this is the most exciting point, it is a very sustainable production through the ambient temperatures that we have, and of course, it's less energy consumption compared to the WFI system by distillation. What systems are necessary to produce WFI by using a membrane-based reverse osmosis system? So actually everything we need is shown on this picture. So the whole entire system is mounted on a single stainless steel frame, and it already includes all the different filtration steps which are necessary to produce WFI, starting with the pre-treatment with filtration and softening, a two-stage RO system. Of course, you can also do it with a single stage, but our point of view is to add another barrier against microbiological contaminations. A membrane degasser, EDI, and ceramic ultrafiltration. And ceramic ultrafiltration is something unique. I will show you in the next slides what's going on with that. And for the entire water quality of WFI, we just need one qualification package for WFI, including storage and distribution. And that means, according to Annex 15, we are able to build up those systems as package units, like pre-qualified in our own workshops, where we do the entire IQ/OQ procedure, and then we ship it, and it's just like plug and play within your workshop to get the systems running. So there's one more thing which is not mentioned on this slide. Compared to the distillation system, if you, let's say, go with a 1,000 liter system per hour, this is the maximum capacity you can reach with the distillation system. A cold WFI system makes you even more flexible, in fact, that these systems can be expandable. So if you know that you need 1,000 liter per hour at the moment, but maybe in 2 or 3 or 4 years you would like to expand the capacity production to double it or even more, depends on the size of the system. This is it's a very easy done job with this kind of technology. Okay, what does that mean for the footprint of cold WFI systems by reverse osmosis in the same company? So we would just need the clean steam generator in this case, then we have the storage and distribution system, no, we come the other way around, and of course the generating system, and that's basically it. There's not more required to produce WFI. So how does it work? To produce membrane-based WFI, we use reverse osmosis with some, let's say, important quality assurance additions. And the feed water, which comes from here, enters a break tank, and then it passes through a, let's say, double-stage microbiological barrier, which is, in this case, a double-stage UV disinfection before entering the softening system and then entering the double-stage RO system. As I said in the beginning, we choose a double-stage RO because the second stage is more or less the purity side, which is, at the end, another barrier against microbiological contamination. And we are even able, in terms of efficiency, by using another concentrate stage, which is not shown on this picture, and also to put in consideration that there is a backflow of the concentrate from the first stage into the break tank. We are able to bring the efficiency of this system, like by water conversion factor for the RO membrane system, up to approximately 90 or 92%. And then, of course, membrane degasser and EDI, that's nothing really special. What's new and unique is that after each of those quality filtration steps, we have a quality dumping system, which measured, let's say, the quality of the water in terms of TOC and also conductivity after each filtration step, after RO, after EDI, and even, which is not shown here, blame on me, after the ultrafiltration system. During production, we can ozonize the ultrafiltration, which is why the ultrafiltration is made of ceramic. Of course, we have two different options. We can use hollow fiber membranes, or we can use ceramic membranes. Ceramic, in terms of investment, it would be higher, of course, but at the end of the day, if we're talking about lifetime, if we're talking about life cycle management for those systems, this one will never be exchanged. So this is running for the next, it runs for the next 20, 30 years, whatever. We also feed partial flow from the concentrate back into the brake tank, so like this one, which has the advantage that the feed water which is required for production comes already in contact with ozone before it passes through the pretreatment. However, the products you produce might be sensitive against ozone, you never know. Even for that case, we have an option, which is another UV disinfection system, which is located pretty close before entering the WFI storage tank. And we can ensure that the ozone which goes through this way for the finished WFI is totally destroyed before it comes into your storage and distribution system. Okay, if the storage tank does not require any further WFI, the system goes into standby mode. Standby for a cold WFI system does not mean that we shut down the system. This would never happen, and this is why we have to make sure that the production, let's say, requirements by your company is as high as possible for those kind of technology. We will always keep the system running. So if there is no requirement by the WFI tank, we will bring the water back into circulation to the brake tank into the complete and entire system. What does it mean? That means that we, at the end of the day, able to bring ozonated water into the brake tank, and then we can switch off the first UV disinfection system to bring the ozone even into the softening system. And we all know that, let's say, the highest risk of contamination is the pretreatment part. The ultrafiltration itself is a redundant system, and we decided to go with a redundant system because we are able to carry out a fully automatic integrity test during ongoing production. So one thing is to have a redundancy during production, so like 50%, 50%, even one of those would fail during the integrity test, you are still able to do the full capacity of production. But the other thing is that you are able to do with one of those in the ongoing process and fully automated suitability test, which is, by the way, automatically recorded in the background by the audit trail system. And if, let's say, the limits of the water that we are going to produce is not reached after any of those quality steps, we would automatically go into the dumping. And the water, or in circulation, and the water would never reach the WFI storage tank. So now, coming to the exciting point, what does it mean for the investment cost of such technologies? So my assumption was that we need a purified generator before to feed the distillation system. And in this case, I said, okay, we have a softening system, we have a purified water generator, and we have a purified water storage and distribution system. We need a multi-effect still for WFI. My assumption was that we're talking about 1,000 liters of production capacity per hour. And then, of course, we would need the WFI storage and distribution system, which means an overall investment of approximately 1.3 million euro. On the other side, on top of this, we calculated maintenance and service cost of approximately 85,000 euro per year. This is just an idea to give you an example. So the important part of the story is this one. Compared to the reverse osmosis system, including softening, EDI, and ultrafiltration systems, including storage and distribution, the overall investment for such a system will be around about 995,000 euro. And on top is a maintenance and service cost of approximately 55,000 euro. When we again try to see everything through the GMP glasses, we also see that the system is in the middle of everything, and the whole procedure is coming around the system. So that means the life cycle management. And even for maintenance and service, we have different, let's say, opportunities available in our service contracts. For example, a shared stock, which means that critical components like EDI, like membrane, RO membranes, membrane degasser, which also have very long lead times, like 30, 40 weeks or even more, and which would also bring your system to a total breakdown, we have on stock. That means that You as a customer, you just pay let's say a fee, a percentage of the purchasing price, and we will ensure that this system's components are always available on stock, and we can bring it even to Turkey within a couple of days together with a technician. Okay, then coming to the calculation of the running costs. So now we've seen the investment cost of those systems. Now we would like to have a more detailed view on the calculation example that I have done. In this case, again, we have a production volume of 1,000 liter, hot and both production. We assume that this is a greenfield project, so there's no other equipment for up or downstream process available. And these are the different types of costs that we have. So we have feed water, electricity, process steam, and compressed air. And these numbers you can see over here is what we currently pay in Germany. So right now I have no clue how it is in Turkey. The green numbers, the green figures over here is what I have put into my calculation. And then of course we also have the wastewater cost, which means wastewater and waste heat. And there's one more idea I would like to give you. By operating a WFI distillation system, you would supply the system with black steam or industrial steam. And industrial steam is usually produced by oil or gas. And to give you an idea what it means to operate a WFI still, heating water to 100 degrees requires approximately 0.116 kilowatt hours. And heating water from 100 to 101 degrees requires approximately 7 times more of energy. And on top of that, the energy content of approximately 1 kilogram heating oil is about 11.4 kilowatt hours, which means that you need at least 65 liters of oil to produce 1 ton of industrial steam. And then coming to the next point, my assumption again, 1 cubic meter per hour, 10 hours a day, 5 days per week. I assume that we have a total production time of approximately 2,500 hours per year. And now we can see that the distillation process means that the price per cubic meter of water for injection is around 113 euro per cubic meter in terms of energy consumption in Germany at the moment. Including service and maintenance, it's around almost 150 euro per cubic meter, which is quite high. And the other way, the opposite would be the co-production of WFI, which means the price per cubic meter of WFI is around about almost 30 euro, and including service and maintenance is around about 50 euro, 51. So, and that brings me back to my first page actually. 25 to 30% less of investment costs. At the same time, we're talking about OPEX, which is approximately 75% less of energy consumption, and approx 30% less running costs for service and maintenance. And this opens new doors in terms of running costs, in terms of energy consumption, and it offers new ways and new paths whenever we talk about sustainable production. And this is a very sustainable production.